Hello everyone, my name is Seheg Bansal and through this presentation we are going to understand a very important mathematical concept known as butterfly effect. Let's begin. We are going to understand what this means. We'll then look at the mathematical explanation and factors, applications in nature, and some takeaways. Butterfly effect. So what does this mean actually? When a tiny variation changes the results of system dramatically over a period of time, the sensitivity towards the tiny change is termed as butterfly effect. Means there might be, okay, let's understand this. We are giving an input into a system and getting some output. If the input is same, the output will be same. That's what we expect. And if the input is changed slightly, like by if there's by just 0.001%, then we expect the output to change only the slightest. But that's not the case in chaotic systems. Even if the input is changed very by a tiny variation, the output can be really different. Let's take an example. Your mom called up twice but didn't pick up. She got furious and called up your dad. She quarreled with your dad and spoiled his mood. In a frenzy, he resigns at his job. Your father took up a project with his company and which his company lost after his resignation. Company faced huge losses due to which they couldn't pay remuneration to its employees. To cover up the losses, the company fired 100 employees. So there was a small event that you didn't pick up your mom's call. The instant effect was she got furious, she got angry. But on a long run, the big change occurred that is 100 people lost livelihood just because you didn't pick up your mom's call. That's how a small event led to a big change. But why is it called butterfly effect? What does butterfly to do with this? Let's understand this, but let's know the history. It was discovered by Edward Lorenz in 1961, who was a meteorology professor. He basically ran a computer model for weather prediction, and he basically put some input, got some output related to the your weather. So by entering some data, he obtained a curve. He changed the input by just 0.127%, and that means he just brought a few changes in the decimal places, and that's really a very small change. So he didn't expect any big change in the curve, but the actual results were really shocking. Initially, both the curves overlapped this way; they were same basically, but later, over a period of time, the results were very different. The curve of both the situations, of both the inputs, they diverged widely by the end of the sequence, as you will be able to see here. So a very tiny change here in the input brought a big change over a period of time. So this difference in the initial points in the initial inputs is very small, and it can be compared. It's so small that it can be compared to a butterfly's flapping, but to a butterfly flapping its wings, and the change caused by it is so drastic that it can be compared to a tornado. So, based on this, in 1972, Phillips Merrilies quoted a few lines which says, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" So, butterfly flaps its wings in Brazil and brings a tornado in Texas. Small event, big change. That's what butterfly effect is. Chaos theory is an umbrella term which has butterfly effect, which is based on butterfly effect. Let's have the mathematical explanation of these chaotic systems now. To understand chaos theory further, we need to have basics of chaotic systems because the whole chaos theory revolves around chaotic systems. We're all aware of linear systems. They're the systems whose graph is a straight line like this. Random systems, they're actually random. We cannot guess their output at all. For chaotic systems, the output is deterministic, but at the same time, it's unpredictable. They're complex and sensitive. This statement seems a bit illogical and ambiguous. So let us have an understanding of what I actually mean by this. Let's have a system in which we are putting the input and getting the output. Let's say the input is 5. For a normal system, the output we are getting is 22.5. If the input is changed by just 0.001, then the output is slightly changed and we get 22.503, which is very close to 5, just like the input is close to the previous input. If the input is doubled, the output is also doubled. If the input is exactly same, the output is also exactly same. That's a very predictable kind of a system, very simple system. Random system, the outputs are very different. If the input is doubled, the output is not doubled. If the input is changed slightly, then also the output is not changed slightly. It's drastically changed, or it might not be changed at all. If the input is exactly same, then also the output is very different. So the random system gives random results, as its name suggests. Now, chaotic systems are interesting. If the output changes slightly, then the output changes drastically. If the input doubles, output does not double. It's very random. But if the input is exactly same, that is 5, the output is also exactly same. Now, we can draw conclusions for chaotic systems that if the input is exactly same, then only the output is same. But if the input changes even slightly, the output drastically changes. That's what butterfly effect. Let's move on to attractors. So attractors is a very important concept in this theory, but it's again at the same time very complicated and not easy to explain this way. So I'll just give you a glimpse of what attractors are. Attractor is a set of points to which a system evolves after long enough time. So if you look at this system, it is attracted towards this single point, and that's why it's called point attractor. Cycle attractor, there's a cycle on which the whole graph goes on and on. So there's no point, but a whole cycle around which the whole graph evolves to. Strange attractors are something very important in chaos theory and butterfly effect because this is basically the graphical representation of butterfly effect only. And if you look at the graph, it somewhat resembles the wings of a butterfly, and that's probably where uh, butterfly effects came from. Applications, if you look at the weather first, the weather that the people predict, that cannot be perfectly accurate. Does not matter how nice machinery or computers or mechanics or process or trained people you're using, but the weather forecasting can never ever be accurate because there are always tiny variations there in the weather which can bring a drastic change in the future conditions. Exchange rates in the stock market cannot be predicted absolutely correctly. Biology. You can't tell how the virus spreads. Did we ever imagine that the coronavirus can spread the way it did? In physics, double pendulum. We're all aware of single pendulum that has a basic oscillatory regular motion. But a double pendulum, this way. This is a double pendulum. There are two pendulums connected. The motion is this. That's not predictable, right? Evolution of life. There was a tiny change initially on Earth that led to the evolution of life, plants, animals, other organisms, creatures, microorganisms, humans, and everyone. Right? The nebula theory brought our Earth, and the Earth brought us. Psychology. A small psychological incident in childhood can lead to depression or even suicide later in life. That's statistically proven that the suicides that people commit are most of the times based on something that happened in their past. So over a period of time, those incidents lead to a big change. Fractals is a very important concept. Fractals is actually they're very beautiful, as we'll be able to see from the pictures on the screen. A fractal is basically a fragmented geometric shape that can be split into parts. Each part is a reduced size copy of the whole shape, and this property is called self-similarity. So basically, if let's take the example of this one, if you take a small part, this again is a reduced size copy of the whole thing. If you take Next time, oh, again a very small part. This is again a reduced size copy. If we further take a part of this is again a very reduced size copy of the whole fern, and this goes on. These are fractals. We can learn a lot from the butterfly effect. Just like butterfly being part of the larger system in nature, we humans are also a part of the larger systems in this universe. We're part of our families, we're part of and the world. So we all interact with each other, we affect one another. Our temperament, our behavior affects each other. So our action today, would have been the result of a previous action, and this would in turn lead to a future action. That small act can change a person's life as well as your life. So a small act of bullying today can become the cause of suicide for another person. Therefore, we should never ever bully anyone. A sorry cannot redo the things. Ovid, a Roman poet, said, "Dripping water hollows out stone not through force but through persistence." Tackle that mountainous task bit by bit and soon it'll be over. And that's why we say practice does make a man perfect. Be consistent and persistent no matter how problematic or tiresome it is. Even with Atharva Veda, we have a verse which says, Ayam loko jalamasit chatrikasya mahato mahan tenaharmindra jale namu sami dadhami sarvi. It means the world is the great net of the great mighty Indra. It is a net made up of connections and interdependencies. So, just like a net, like different things are interconnected, different strings are connected to each other. We are the strings of this world, we creatures, we humans, all organisms are the strings of this web, and we all are interdependent on each other. That's how it shows sensitive dependence on initial conditions. That was all. Thank you very much, and I hope you learned something new from this presentation. Thank you again.